Graphite nanoparticles were synthesized using a sodium hydroxide-assisted electrochemical approach in a single container, with graphite pencil as the carbon source and current of 16 to 78 milliamperes. The GNPs were characterized by high-resolution transmission electron microscopy, infrared spectroscopy, absorption, and photoluminescence spectroscopy. HRTM revealed lattice spacings of 0.336 nanometers and diversity particle sizes. Absorption showed a monotonic behavior in absorbance intensity as the current increased and revealed absorption peaks typical of graphitic materials. The PL emission spectra exhibited a red shift with decreasing PL intensity as the excitation wavelength increased, consistent with previous reports. The PL exhibited a red shift as the synthesis current increased. According to our experimental observations, the PL emission of the GNPs is more closely linked to the QC than to surface states and governs a much broader range of PL emission wavelengths, whereas surface states have a more limited influence. Fluorescence related to surface conditions and functional groups has been widely reported and investigated. Surface characteristics, such as the degree of oxidation and the presence of functional groups, directly influence the fluorescence of carbon quantum dots. Furthermore, surface engineering of carbon quantum dots has been explored to achieve controllable luminescence, and various synthesis techniques have been developed to functionalize them with surface groups. Variability in manufacturing processes leads to differences in surface functionalization, which modulates their photoluminescence. This modulation results in a broad range of emissions, spanning both the visible and near-infrared regions. However, a limited number of studies have explored the origin of emissions associated with QC in GNPs. Some methods have been reported to vary the size of CDs and thereby modulate the band gap, and controlled electrochemical methods using current have been adopted to control CD size, as described in. We synthesized GNPs of various sizes to evaluate the impact of QC on their PL and investigated their PL emissions, including optical and structural characterizations. It is noteworthy that during the synthesis of the carbon nanoparticle samples, we maintained constant growth and purification conditions to minimize variations in surface oxidation and functional group modifications among the samples, thereby reducing the influence of surface states on PL emission. The GNPs were synthesized by means of an electrochemical approach in graphite pencil rods as the carbon source, and use it as electrodes in an electrochemical cell. Through careful synthesis and purification, we successfully obtained GNPs using this electrochemical procedure, achieving emission ranging from violet to red, 400 to 700 nanometers. HRTM images analysis showed that the resulting GNPs were well dispersed with excellent solubility, and the particle size, measured by counting 10-15 individual nanoparticles, revealed a size distribution with mean sizes of 2.44, 3.66, 3.91, and 6.80 nanometers, as determined by statistical image analysis of the 4 samples. HRTM shows an individual nanoparticle from the sample prepared at 48 milliamperes, displaying average lattice fringe spacings of 0.336 nanometers obtained by fast Fourier transform analysis using digital micrograph software. This spacing is consistent with the interlayer spacing of a graphitic structure corresponding to the 002 crystallographic plane. In the UV-vis absorption spectra, 2 absorption bands are identified in the 200 to 320 nanometers region and 1 band in the 350 to 400 nanometers region. There are 2 peaks located around 230 and 280 nanometers, which correspond to the pi asterisk transitions of aromatic C equals CSP superscript 2, hybridized graphitic domains, and N pi asterisk transitions associated with oxygen-containing functional groups, such as carbonyl and carboxyl species, respectively. In the low energy, a broad peak appears in the region 330 to 400 nanometers, related to N-pi asterisk electronic transitions of oxygen-containing functional groups together with transitions involving defect-related states and extended pi-conjugated domains, indicating that the nanoparticles are not composed of a single component, but rather a mixture that reflects the heterogeneous surface chemistry of the GNPs, arising from the coexistence of different oxygen-containing functional groups and graphitic domains. As shown in the UV-Vis spectra, the peaks exhibited no shift in their position. However, a decrease in UV-Vis absorption intensity was observed as the current was raised from 16 to 78 milliamperes. This observation coincided with an increase in the average diameter of the GNPs from 2.44 nanometers at 16 milliamperes to 6.80 nanometers at 78 milliamperes. The decrease in absorption intensity with increasing synthesis current can be explained by the quantum confinement effect. Smaller GNPs exhibit stronger quantum confinement, which results in a larger band gap and consequently a higher density of electronic states available for UV-Vis transitions. As the GNPs increase in size, quantum confinement weakens, their band gap decreases, and their electronic structure approaches that of bulk graphite, which has a lower density of states in the energy range of the UV-Vis region. Therefore, the probability of electronic transitions in this spectral range decreases, resulting in lower optical absorption intensity. Simultaneously, the increase in current intensity induced the aggregation of the GNPs, which led to the notable decrease in absorption intensity. This phenomenon occurs because aggregation involves the physical clustering of nanoparticles, creating a collective system where individual electron clouds interact. The unchanged absorption peak positions confirm that the fundamental chemical structure of the individual nanoparticles remains intact as the synthesis current is varied. FTIR spectra measured to investigate the surface chemistry of the GNPs. No significant differences were observed among the purified samples, either in peak position or in the percentage of transmittance, indicating a similar surface chemistry. The spectra revealed the presence of the same functional groups in all the samples, such as CO stretching vibrations, 1078 cm superscript 1, carboxylate groups, and or C, H bending vibrations, 1387 cm superscript 1, aliphatic, CH3/CH2 stretching vibrations, 2970 to 2820 cm superscript 1, and two absorption bands centered at 3260 cm superscript 1 and 3446 cm superscript 1 were assigned to O. H stretching vibrations associated with strongly hydrogen-bonded hydroxyl species and surface hydroxyl groups, respectively. The oxygen-containing functional groups and graphitic domains are consistent with the broad absorption band observed in the 330 to 400 nanometers region of the UV-Vis spectra. The band at 1580 cm superscript 1 corresponds to C equals C stretching vibration of sp superscript 2, hybridized carbon atoms, confirming the graphitic structure of the GNPs. This assignment is consistent with the UV-Vis analysis. The peaks identified in each sample are located at the same wave number, indicating that the surface states of the GNPs are essentially the same in each case. It is well known that the PL emission of GNPs is strongly influenced by surface functional groups. For the purposes of this study, the SFGs were intentionally unchanged across all samples, with the average nanoparticle size considered as the only variable. In previous studies, photoluminescence, PL, emission bands of GQDs have been identified. In this work, the He GNPs with different size distributions were synthesized to investigate size-dependent emission without changing the surface oxidation or altering the surface functional groups during the size variation. The aim of this approach was to minimize, as far as possible, the influence of PL emission from surface states. The four investigated GNP samples, with mean sizes of 2.44, 3.66, 3.91, and 6.80 nanometers, exhibited broad PL emissions peaking at 465, 475, 505, and 535 nanometers, which correspond to energies of 2.66, 2.61, 2.45, and 2.31 electron volts, respectively. The emission profile was complex and spanned the visible range due to the overlap of multiple PL bands, a result of the sample's size distribution and diversity of functional groups. Normalized PL spectra of the GNPs obtained a current of 16, 32, 48, and 78 milliamperes. The PL spectra demonstrates that the current affected the PL emission wavelength. Smaller nanoparticles were observed at lower currents, while larger nanoparticles were found at higher current. This result suggests that high currents promote a more aggressive exfoliation process, producing larger nanoparticles with a greater tendency to agglomerate. The increase in current involves an increase in current density, which favors greater intercalation of ionic species between the graphite layers, generating particles with larger average sizes and broader size distributions. In particular, the increase in nanoparticle size up to 6.80 nanometers at 78 milliamperes reveals that at high currents, rapid graphite erosion and possible coalescence or aggregation processes between nanoparticles predominated. This indicates that the current applied in the electrochemical exfoliation of graphite plays a fundamental role in the size of GNPs and is a determining parameter for nanoparticle size control during the electrochemical exfoliation of graphite in a medium composed of NaOH and citric acid. Higher emission energies were observed for smaller GNPs, while lower emission energies were found for larger nanoparticle. In energy words, the band gap gradually decreases as the size of the GNPs increases. This explains that the PL emission originates from the quantum confinement effect, QC, occurring in the GNP's core, as is typically the case in semiconductor quantum dots, QDs. The carbon core is composed of a pi electron system, which could be strongly coupled with surface electronic states, thereby modifying the PL emission of the GNPs, figure 3. Both the states resulting from the QC and the surface states would be jointly responsible for the PL emission. It can be strongly inferred that the size plays a much more significant role in the PL emission and band gap modification than the functional groups on the surface. As the size of the graphite core increases, the pi electron system expands, reducing the energy gap between HOMO and LUMO. We believe that the QC plays a more prominent role than the surface states, which are mainly influenced by functional groups. According to our experimental observations, the PL emission of the GNPs is more closely linked with the QC than with surface states. The QC governs a much broader range of PL emission wavelengths, whereas surface states have a more limited influence.